Hello, welcome to another problem session. So today we have another standard problem from Ampere's law applications. Uh, in this problem, you have a physical. This is the physical system where you can think of a box where you kind of winding wire, and then one side, and all current is running in the same direction. And then you want a magnetic field at a distance d from the plane. So this will be physical, but this is the ideal, this idealized version, which is what we're going to solve. Even we're going to solve even more idealized than that. So the current is going, say, along the y-axis, okay? So this is you might think of this as xy plane. Here's the origin. Now this is going infinite in every direction. So it's infinite in every direction. And that's what we say, the current has a planar symmetry, just a name. That's what we mean when we say in Ampere's law situation, this is a planar symmetry. And you will see the application, how this is going to be. So let's look at one of the wires. So how do I get the magnetic field at point P, right? So when we apply Ampere's law, we are trying to solve this problem. We're trying to actually set up this problem on some kind of closed oriented loop in space. So this, and once we do this, this should equal to mu naught times I enclosed. Right? So this is what we're trying to set up. And in setting up, somehow B kind of comes out of integral somehow with a choice of appropriate choice and arguments for that. This leads to B equals to something, okay? B at say point P something. So that's the idea. So the argument goes, the very first step of the argument is using Biot-Savart law. So Biot-Savart law will tell us a whole bunch about these things. So one is, say if we look at a current, say parting, going at some point distance a on the x-axis and distance minus a. So look at these two currents. So maybe this thing is going at A, but the physical wire, maybe not any of the wire going at minus A. So that's going to be a problem. So we kind of make this into a continuous, and that's where the tightly wound comes. If the wires are tightly wound, then we can just forget that they have a physical wiring. And you can just say, well, just current just flows in that direction. Well, so we have to assign some kind of current value, right? So suppose there were on this thing along the x-axis, if I go, there were n wires per unit length of x-axis, which is perpendicular to the current axis, right? The current is going along the y, so this is perpendicular current axis. So if you look at one unit of the x-axis, so how much current is passing through a single unit? So amount of current passing So this is perpendicular, and this distance is, say, L over L. This is the amount of current. So L in the perpendicular to the current direction per unit cross section length. So this thing is actually called surface current density. Is called surface current density, and usually we use a capital letter K for that. So in this situation, for us, you have a n amount of wire going through I, n times L perpendicular, and each one of the wires is carrying current I. So this number of wires per unit length, and that's the length. So that's the total current that went through I total, and this I in each wire divided by L. So you can see that this is just simply equal to how many wires per unit length perpendicular to the wire times I in each wire, which can just call I. So this is equal to K here. Okay, so you can just say Ni. Let me erase this and get the next argument. Okay, so we take in a small delta x, maybe at a distance a from, and you take a current in the same amount of distance of delta x and same distance a on the other side. So this current, let's call it di, it will be same amount over here. This will be equal. And when you look at this current using right hand rule from, so this will be right hand rule from the Biot-Savart law, it will tell me that it's going to be perpendicular to that and perpendicular to that line. So it's going to be B from, say this is B from 1 and this is 2. B from 1 will be like that, and because small current is going to be like a dB1, and dB from this guy will be perpendicular to this, and to this is going to be exactly like that, dB2, and magnitude will be this dB1 will be equal to dB2 because they're the same. Of course, this thing is, going, I assume to be going in infinite direction. So this is infinite wire. It's going to go circular around this, right? It's going to be part of this, and this guy is also going, so it's also, did I do it correctly? This, and so I do right hand rule, and so it's going this way, and then right hand rule from here going that way. So actually I did not do it right. So this one is that way and this one is that way. Okay, so dB1 is, dB2 is not that way. This is dB2, sorry about that. And dB1 is that way. They're equal to each other. So if you look at their z components, dB1z equals to minus dB2z. So when your dB1z plus dB2z equal to 0, so this, the net field will be in the xz plane. Current is going along the y-axis. So if you look at the xz plane, it's going to be like that. Oh, sorry, but let me erase this. And okay, so I got some cleaned up here. So in pink here, there's the xz plane. So magnetic field from current in this part and current in that part. Magnetic from this is in that direction. Magnetic from this is circle around, and so this is tangent to that circle. And so it only has the net is along the x-axis. Is equals to some dB and I hat. That. So you can write the Biot-Savart law and integrate and everything, but we're not going to do it. But it just is going to be, so this tells me at P, B is towards x-axis. It can be it has a positive x-axis for us. This is the x-axis, and this was the y-axis for us, right-hand coordinate system. Now for these two, I got I hat. For every all of this on the right side, okay, has corresponding thing on the left side, right? Will be somewhere. If you take another little thing, it's going to be corresponding or match with that, will give me the same result. And that's why it's infinite plane is needed. That's why this is infinite plane. So in infinite plane, there's always going to be matching, right? If you have finite plane, then this will happen on on this z-axis, symmetrically placed. But if in infinite place, this will happen at every point. So above the plane, all are positive direction pointed this way. Now, if you look at the below the plane, all the magnetic field will be pointed that way. This will be the magnetic field pointed that way. So we got the direction. So towards the x-axis, above the current, and towards negative x-axis, below the current. Okay, so we got the direction. Now, if I have a situation where the current is like this, then it can't depend on every x and y. So if I look at this where the current is, if I look at all the points at a distance d, so this is the point P is over here, but I look at every single point here. Now this point will have one x equal to 3 and y equals to 4 and z equals to d, and this point may have minus 2 and 3 and maybe d. Now they all because this is going to infinite in each direction, they're indistinguishable from the perspective of this symmetry. That's why we call it planar symmetry, because we got infinite extent. So so the other claim is the B at any point P with a coordinate x, y, z, say P is at x, y, z, okay, then B can only be a function of z, can't be a function of x or y. And that has to do with since current are on entire xy plane. So using these two, we should be able to Yeah, sorry about that. There was a little phone I had to really take. Okay, so there's a couple of really important conclusions you can draw from one from Biot-Savart law, right? This direction you can't get from here. You got to go to Biot-Savart law to get the direction. And then this is a important observation, and that's going to be system by system, right? In this system, it's the case that it can't depend on x and y, which means if I go up here or go over here, if you draw a line, magnetic field will be same on that every point on that line. So this line here that I have to decide on what loop to pick, this DL, it helps to know which way the current is going. So imagine this is the x direction, this is the x direction, and the current is going y direction. So I could draw one of the loops could be in y-axis, or it could be along the x-axis, right? This could be part of the loop. This is not a loop yet, but the B will be the same here. Now, really interesting observation this is, if I go below this same distance, so this is D, and I could go, so this is parallel to this. So I could go this way or this way, you know, along the y direction or the x direction. Now, if I take a plane, really same distance d down here, well, it doesn't depend on z. I mean, it depends on z. The only thing that depends on is z. So if the z is the same amount, then on this also all these points will be the same, right? So I could see if I took a loop along the y-axis, I can try to see if I can make a loop out of it. It's the same color. Let's use one color for along the y-axis. So this could be, and I use the that I can have that loop, but actually that doesn't capture the B at all. It has no current going through it, and so it's really not going to be helpful. So what we do is, the magnetic field was in that direction anyway, so just go in that direction, the magnetic field over here. That's what we want, and we go right through the x-axis and right through there, and then we just go this way, and then we have all these currents down here in the middle. We have the current is crossing through there, that's included, right? So we can go this, and then this, and then this, and then this. So this will be the A, B, C, and D. Maybe I can use another color. A, B, C, and D. So that will be the loop. And so this is a loop that's in the XZ plane. So that means we take a loop in the XZ plane. A, B, C, D, and then the current will go right through it, and you can see that if I take a right hand rule, then the if the loop is okay. Let me erase some of this because I am running out of space here. Okay, so doing this integral on this oriented loop a b c d a, b dot dl, this go a to b, b to c, c to d, d back to a. So a to b, you remember this is the direction of the b field also here, right? B is in that direction and dl is in that direction. So this just I need to just get a length of this, how big that is. So this rectangular shape, let's call it length L from here to here. So this is it's going to be whatever the b at that point is, b at p. So b at p, p is that point p. It goes right through the p. Just take it like this, arbitrary. How about over here? Over here dl is that way, but we already argued that if you're above, right, if you're above the then it's all positive x direction. So b is, if you look at that element, b dot dl is 0, so that's going to be 0, and then we're gonna all the way, it's gonna all be 0, and then c to d, we know that b in this goes in that direction, and dl, the direction I'm going, is in the same direction. So that's also actually this is a plus, and this point has the same distance, so it's got the b is equal to b at p. So if this is p prime, so b at p prime is same as bp, and all of these are equal to b at p prime, right? So it's going to be b at p and same length L, and when I go up here, it's going to be 0 again for the same reason as that. dl is that way, and the b is that way over here, is perpendicular to each other, and it's going to be 0. So what I got here is 2 times b at p times L. So how much current is enclosed? Well, we K times L, right? So I enclosed is K times L, and K is just number of lines, wires that's going through times how much each wire is carrying. So N equals to number of wires per unit length, and I is the current in each wire. So using the Ampere's law, P dot dl equals to mu 0 times I enclosed, we get 2 times bpl equals mu 0 kl, and that's cancelled out, and so bp equals to mu 0 k over 2, and the direction is this way, above this and below the direction. So direction is in the picture. Interesting thing is, it doesn't depend on z. So interesting thing is, doesn't depend on, it's really constant. So it's the same everywhere. The direction depends on you're above the plane or below the plane. And if you write down in terms of number of lines and I, this will be just equal to, this will just be equal to mu 0 ni over 2. Now let me make a note of that relationship of this with what we saw in the solenoid. Okay, in the solenoid you saw that when R is finite, only the inside you have a non-zero, and it is The formula was given by this, right? Outside is 0. So imagine as you make R bigger and bigger, okay? So if I take a R, go to infinite limit, then while we keep this point, the distance from this fixed, I keep this point fixed, I just make this guy bigger and bigger solenoid, bigger and bigger solenoid, bigger and bigger solenoid. Eventually this will become like a plane. So this and the point P will be kind of next to it, you know, point P will be next to it, and this plane will go to infinity. And while this guy was 0, now you not only have the magnetic field over here, but you got a magnetic field over here too. So this was like a P prime. So P prime, now B at P prime is not 0 anymore. And so you might say that this is half the magnetic field used to be here. So the magnetic field is kind of distributed. But this is interesting. Can you actually set it up mathematically, take R, go to infinite limit, and get this result? That's a pretty hard problem. So over here, B at P is mu naught Ni over 2. And over here is mu naught Ni. With that, I'm going to stop. Just remind you to subscribe to this channel. You might get reminded when new videos get posted. You might enjoy them. And if you like it, please hit a like button. I appreciate that. Thank you. And you may want to check out my website with a lot more problems there solved for you to practice, okay? And many more problems to practice. Thank you and bye.